Okay, so today we're going to discuss a new topic, which is shapes, and this is the last technical topic of the course. Well, I'll actually upload a class on another topic, but we'll be using the remaining time in the course for projects. So shapes. Um, Before we spoke about the semantic web, the overall structure where we have data, logic, query, and output. You've seen this slide many times. There's one remaining aspect, which is a major challenge for the web in general, which is that of data quality. How can we assure some basic data quality if we're exchanging data on the web? And well, for graphs in particular, that can be a bit of a challenging topic because we have essentially this very flexible structure, right? So we don't have to impose a schema from the start. And this is actually quite useful. If we compare it with relational databases, it's a lot more flexible. We can just add nodes and add edges and add labels on those edges and continue in that way, in a very flexible way, describing our data. However, the disadvantage of this is that we lose the structure, the schema that we had imposed. So we don't have such a good structure as we would in a relational schema. Okay, so we have this very flexible structure that somehow eventually the structure itself is organic. A structure will emerge if people follow the same principles and use the same edge labels to mean the same things and link to the same nodes instead of creating duplicate ones. Then we have this sort of organic structure that emerges from the graph. However, if we want to, even if we have graph data, we can impose a schema. It's not that we don't have, we just have to ignore a schema. We can impose a schema anytime we like. And the question is, what sort of schema can we impose on a graph? So how can we define and impose a schema for graphs is the question. And if we had somehow this optional schema, we'd have the best of both worlds. We'd have maybe more structure like we have in the relational database setting, but we would also have the flexibility of not having to define a schema at the outset, at the start. So the answer for how to define schema, how to define a schema for graphs, essentially is the notion of shapes. And shapes allow us to validate graphs. So it's a bit different from RDF schema, which for me is not really a schema. It's just an ontology, a lightweight ontology language. It's a bit different from OWL and it's a bit different from Sparkle, which we've seen, and I'll explain that in a little bit. But its core purpose is to validate graphs. So we have here some graph of data describing some movies with some Academy Awards. And essentially we want to ask, is this a good graph? Is this complete? Are we missing some important facts here? Is this sufficient for our application? Maybe we're building a movie database application and we want to ensure that the descriptions we include are complete from the web. So is this graph complete? Does it have any errors, any problems? How do we define these notions of completeness and errors? So the answer is to build a shapes graph, or to use shapes to describe precisely what we mean by complete and what we mean by error-free. And the shapes themselves follow a graph as well, in a way. So what we have here is an illustration of a shapes graph. And we see that we have different shapes: award, Academy Best Picture, Academy Best Director, movie in person, 5 shapes. And we see that each shape defines some restrictions on data type properties. So these are the things that take strings or dates or Booleans. So it says here that a person has one or more names, which must be a language string. It has precisely one date of birth, okay? A movie has 1 year, which is an instance of the data type G year. It has a short, whether it's a short movie or a feature length movie, and that's a Boolean, which is optional, 0 or 1. And we have name, which is, again, one or more names with maybe different languages. Same here, must have a year, must have a name. Okay. So the next thing is we can connect the shapes, and we can say that an award must have 0 or more judges, can have 0 or more judges who are persons. Okay, and all judges must be people. The Academy Award must have a nomination for 0 or more people nominated for it, 0 or more people who win it. We say zero or more here because some Academy Awards might be won actually by movies. So an Academy Award must be associated with at least one movie, because even if a person wins, it must, that person must have worked on some movie and must be won by some movie. So we have one or more here. This here represents a hierarchy, which says that essentially the shapes here must satisfy not just the details here, but also the details of the shapes that they inherit. So Academy Best Picture must inherit all of the restrictions on Academy Award, these 4 here, and it must satisfy the 3 restrictions on award, having a year, a name, and having all its judges are people. So this is the shapes graph. And there's one aspect to highlight, which is that here these counts, this doesn't say that it must have 1 year that's a G year. It says that it must have 1 year and all of its years must be a G year. So somehow the count and the type are separate. But it's a subtle point for now. Okay, same here, for example. So it says that all of the nominated persons must be persons, people, and there can be 0 or many nominated persons. So if we take this graph and we look at the shapes graph and we ask, is this graph here, this RDF graph, valid according to the shapes graph? Does it pass? That's kind of tricky. So the first question is, okay, how do we relate the shapes to the graph? How do we know that person somehow should apply to the people, right? So how do we connect, say this shape should apply to this node here, or that movie should apply to this node here? How do we connect the shapes to the nodes? So right now it passes because we haven't done that. And we haven't connected the shapes yet to the nodes in the graph. So it means that we haven't defined what's called a target for the shapes. So we don't know which shapes apply to which nodes in the data. So if there is no target, then it means that we're not applying any shape to any node, and therefore it kind of passes trivially. So, okay, how do we define a target is the next question. So to define a target, there's multiple ways, but here we will just say for the moment that we're going to target anything that's of type movie with the movie shape. Okay, seems kind of intuitive in this case. So we'll say, okay, anything that's a movie, we're going to check with this shape. So now we're going to be targeting parasite with the movie shape because parasite is of type movie. Okay, so we denote it in pink, the targeted shape. So we now have to check the restrictions on movie, where it says that every movie must have a year and it must have a G year. So we see that's fine. Must have a short, sorry, it can optionally have a short. If it has a short, it must be a Boolean. So we see no short, but that's okay because it's 0 to 1. It can have 1 or more names. That should be language strings. And we see that it has 1 name. So that's enough to satisfy this constraint. And then we look at the other constraints. So director, so it must have 1 or more directors. Yes, that's fine. And that director must have a name. It must satisfy the person shape. So it means Dabong Jonhu. I'm not sure about my pronunciation, sorry. Should have a name and a date of birth. And that's not the case here. So the director of the movie does not have a name nor a date of birth. So this means effectively that the shape will fail. So parasite itself, the movie, satisfies the local movie shape, but not the linked person shape for director. So we're missing a name and a date of birth for the director. Any questions or doubts? If not, we'll continue. So multiplicity is the next thing to consider. So just to note that if we have a director 0 to 0 or more, as I mentioned before, this doesn't mean that we have 0 or more directors that satisfy the person shape. It means that we can have 0 or more directors and all directors must satisfy the person shape. So if we look at this example again, the only thing we've changed is the 1 to a 0. Okay, so and then if we ask, does this satisfy the shape? Then we say no, still. So it does have 0 or more directors that satisfy the person shape. It has 0 directors that satisfy the person shape, right? But it has a director. And this means really that every director must satisfy the person shape. So we're still in the same problem. We're still missing the name and the date of birth for the director. So it still doesn't satisfy the, even though we have 0, it says here 0 or more. Even though it says that if there is a director, it still has to satisfy the person shape. So just to clarify that. Okay, if we add a name and a date of birth for the director, and the date of birth is a date, and the name is a language string, are we good now? And the answer is that, yeah, we're good. So now Parasite satisfies the movie shape because it satisfies it locally and the director satisfies the person shape. So we're good. Okay. So to briefly distinguish between what we've seen before, why do we need something new, right? We already have RDFS and OWL, and we already have Sparkle. So versus RDFS and OWL, there are some similarities in that in OWL, we can define lots of things. We can say that an award must have all values from G year, all of its years must be a data types G year, that it can have, it must have precisely 1 year, that it must have always language strings as names, that it must have at least one name, that it must have all of its judges must be people. We can do something similar for our Academy Award. So effectively, we can define something very, very similar to what we're intuitively describing here in OWL. Okay. The major difference is that in OWL, we apply interpretations. And, when we count things, we're actually counting, for example, names, or we're counting movies, or we're counting people. We're not counting nodes in the graph. And since we can have multiple names that refer to one movie, we have to take this into consideration. And also, given that the data can be incomplete, we have to take that into consideration as well. So in OWL, we apply a sort of semantic interpretation, and we allow that multiple names can refer to the same thing, and that the data can be incomplete, that there can be things we're not fully describing. So because of this, because of the open world assumption, where we assume data are incomplete, and no unique name assumption, where we assume that many things could refer to one thing, many names could refer to one thing, we cannot easily detect missing data or duplicated values. So it's this sort of at least one problem, right? So if we have 5 children, then we can say, okay, there's at least one child, but that's not really what we'd like to do when we're validating the data itself, the graph itself. So the difference here is that in shapes, we're applying counts on nodes in the graph, not people who are children, right? So it's operating at a different level here. So we're counting nodes and triples and so forth here. We're not interpreting them and counting movies or whatever. We're just counting how many nodes does an Academy Award have as a movie that won. Sparkle operates at the same level of shapes, which is to say Sparkle, if we do a count for children in Sparkle, it will say 5 because there's 5 nodes in that position, right? It won't tell us at least 1. So Sparkle and shapes operate at the same level, which is at the level of the data, the level of the graph, the nodes, the edges, and so forth. And we could do something similar in Sparkle. We could write these constraint violations as Sparkle queries and say, okay, anything that's returned as a result for the Sparkle query is breaking our data somehow. There's some problem here. So here, this is the constraint for movie. Effectively, this is equivalent to what we have here. We're targeting type movie, so we just put that at the start of the query, and then we try to find some years. Okay, And then we check to make sure that we try to make sure that there is at least 1 year here, or it's, so we find movies where there's no year, okay, or where the years, some year is not a G year, or where year one is not equal to year two, which means that there's at least 2 years when there should be precisely one, and so forth. So here we can return movies that somehow break the constraints that we have here. This is not complete, by the way. This is only later. We'd have to check that the director here has satisfies the person shape. As we see, it's a bit of a nightmare. It's sort of difficult. We have all these optionals to check if something exists or not, if there's 2 or more of them, what the types are. So writing these queries is far from straightforward. So although we could do something very similar in Sparkle, and there is actually work that will translate from shapes to Sparkle, the idea is that it's a bit difficult it's not so intuitive. You need to be quite expert on Sparkle to be able to write these constraints directly in Sparkle. So somehow shapes should be a more direct and easier way to express these sorts of restrictions on the graph that we can then validate. Okay, any questions or doubts? Just gonna check the time. Oh, we're good. Okay, so there are 2 proposals for how to express shapes over RDF data. And the one that's standard, that's become a W3C recommendation, and thus a web standard, is the Shackle language, which stands for Shapes Constraint Language, SHACL. So here we saw sort of a pictorial representation of a shapes graph. And then the question is, okay, how are we going to write that down? So how do we define shapes graph? Shapes graphs. So the response to that is, since essentially we're on the semantic web, the Shackle's response to that at least is, okay, we can think about using RDF. So what we need then, if we're going to describe these shapes in RDF itself, is a vocabulary that we can interpret as restrictions, as constraints on an RDF graph. So this vocabulary and what it means was standardized in 2017. So it's one of the more recent standards that we discuss. So we have our shapes graph here, and what we'll start to define is just bit by bit what it looks like in Shackle. And we'll do that in Turtle syntax. So we see that we're describing this shapes graph as RDF. So it's sort of like we're using RDF to validate RDF, right? So we have person here, where we have a node shape, and I'll go into more detail later on what these mean, but we'll just see the serialization for now to get a flavor. So we have node shapes, which are essentially these boxes here, these shapes here. And then we say that, okay, what do we need to define for person? We need to define that it has 1 or more name, and that all names are language strings, and that it has exactly 1 date of birth, and all date of births are types, or the date of birth is a type, is a date, sorry, data type. So we say person is a node shape. It represents one of these boxes. And then we say it has properties. Okay, it has 1 property, and then we define the path of that property. So we say name. So on the property name, we must have a language string, and we must have at least 1 name. It's the first element here. Second element, we say that there's a property, date of birth, must have the data type date, and there must be at least 1 and at most 1. So we define the min and the max to be 1, which means the count will be 1. So this allows us to define the shape here in Shackle. We'll move to the movie example, which is interesting mainly because it has this extra thing here. So we have a movie, which again is a node shape, and we again define some restrictions on the year, whether it's a short movie or a long movie. In this case, we just put a max count of 1. So this means that the default is 0, and the max count default is infinite. So here we put a max count of 1. So this then means 0 or 1. We put the name. And the last thing, the interesting part here is the director. So we specify a director and we say that the director must correspond to the person shape that we defined earlier, right? And then we say there must be at least one director. So this is the new part here. We use this node edge to say that this movie on the director property, it must satisfy person, the person shape that we defined earlier. And okay, if we want to define a target and say, okay, this movie shape must target instances of movie, then we can use this target class feature of Shackle. Moving to award, it's kind of similar, so I won't go into too much detail, but we specify the restriction on the year, specify restriction on the name property, specify restriction on the judge property, saying that the judge must be a person. And we notice here that we don't put any counts because here it's 0 or more, and that's the default case. So we don't need to, it would be redundant here to specify, for example, the min count. The max count by default is infinite. Academy Award is a slightly more interesting case because we have this inheritance of the shape here. So how we define this is we've defined person, movie, and award, right? With these three shapes here. When we come to define Academy Award, we define node award, which means that we're going to apply all of the restrictions we define for award. So this is the interesting part here. So we define node award directly on the node shape, which says that Academy Award inherits somehow the award shape. And then we apply the usual restrictions on the properties. So non-person must be a person, win person must be a person, non-movie must be a movie, must satisfy the movie shape, and there must be at least one of them, and same for win movie. And finally, we have Academy Best Picture and Academy Best Director, which are just inheriting the Academy Award shape. So we just say, okay, you must, any Academy Best Picture must satisfy the Academy Award, and any Academy Best Director must satisfy the Academy Award shape. And this is essentially how in Shackle we would describe and serialize, write down this shapes graph. So we write it down in RDF. And then we'll have special processors that will be able to take that Shackle RDF description and or RDF graph describing movies and awards and so forth, and then validate the RDF graph with respect to the shapes graph described in Shackle. Any questions or doubts? Let me see how we go. Okay, so in terms of targets, how we target, we're going to get into more detail. We saw sort of like an initial example to give you the flavor of what we can do. So we'll jump into the different language features of Shackle now. So the first thing is how to define targets. And this is where we say that this shape must be applied to these nodes here in the graph, right? So to be able to map the shapes to the nodes that they apply to. So there are 4 ways we can do this in Shackle. The most obvious one is target class. So this is where we say, okay, the movie shape should target the movie class, right? It's very, very intuitive. So this also will target subclasses of movie, which we'll see in a second. However, we might not have one class that we want to target. Sometimes we might want to target the subjects of a given property. So target all of the nodes that have won an Academy Award, for example, or target all the subjects of works at, right? So these would be all the employees, for example. Target objects of the opposite, works at, then the objects of that would be the companies where people work, for example. Target node. This would be then to target one specific node that we want to validate, which would be less often used, I would say, but okay. Still, you can do it. So, okay, so here we saw already how we can target movie. So this time we're going to target objects of a property. So we're going to say all of the objects of win person property in the RDF graph, we're going to target those. So it's essentially saying, let's target all of the people who've won an award effectively, or who have won something, right? So all of the people who have won something, we're going to apply this restriction to that. Okay. So we're going to make sure that the name is a language string and there's at least one of them. And we're going to make sure that every date of birth is a date and there's exactly one of them per person. So if we have our data here, we see that since Bong Jong-hoo is a director, sorry, no, that's not, is a object of win person, okay? Since they're the object of win person, it means that they will be targeted by the shape here, okay? So then we check that they have a name and they have a date of birth, and we see that they do, so we're good. Okay, so we can target the objects of a given property. In this case, we're targeting all objects of director. In this case, there's only one. We could also target subjects, right? We could target all the subjects of name, for example, which would be Parasite, Bong Joon-ho, and that would be it, I guess, or all the subjects of Win Movie, which would be Academy Best Picture 2020, Academy Best Director 2020. So we can pick the domain range. In terms of the subclasses, here we can specify the type and instance in the graph. So we use target class for that. So we specify that the award shape should target the class award, all of the instances of award in our RDF graph. So if we have here two nodes, what's interesting here is that they're not directly instances of award. However, they are instances of Academy Best Picture and Academy Best Director, respectively, which themselves are subclasses of Academy Award, which themselves are subclasses of award. So Shackle will also include these subclasses here. So essentially, these shapes will be targeted because they are through the subclass relation. They are instances of award. So they will be targeted by the shape. And then we check the year and the name, and we see that we have a year here, and we have a name. We don't have names. So if we come to ask, is this valid or not? We'll say no, because we're missing at least we're missing the names. We might also have other problems, but every award should have a name here. So, and that's not the case. Okay, so these are invalid, both of them. Any questions or doubts? Okay, so we're at 10:45, so we can take a 10-minute break and we'll continue. I'm not 100% sure we'll get the full class done today, but if not, we can finish it on Wednesday. So see you in 10 minutes. Okay, so the next feature we have in Shackle, after targets, we have paths. So in the example so far, we've seen a direct property used on the path, but we can also specify property paths from Sparkle to be able to validate not just values directly on properties, but also things that are connected from the current node, the current shape, via a path. So we can have a property, an inverse of a property, which we need to write in RDF. So we use turtle for this. So this is the inverse of path of E, the inverse of E, which in Sparkle looks like this. We can have a sequence, so E followed by F, where we write E/F in Sparkle. An alternative path, which is E or F, which we write in Sparkle like this. 0 or more path of E. So this is E star. This is called clean star. 1 or more E, which we write as E plus, clean plus in Sparkle, or 0 or 1 path of E. So that's essentially the node itself, or a node that's connected to that node by E, and that's E question mark. So essentially we can validate also nodes that are connected to the current node via a property path, and say, for example, that they must satisfy some other shape. So we have an example of that here, where what we're saying is that the Academy Best Director, we're going to target the class Academy Best Director. So what we're going to then say is that the movie that wins this and the director of that movie must satisfy the Academy Award winning director. So it must, if there is a director who has won an Academy Award for this, then they must have a name and a date of birth. And the name and the date of birth, or this shape here in the other direction, must have won an Academy Best Director. Okay, so we write it like this in the shackle. So we say path here. We use just a list. So we say win movie followed by director. That's how we write this path here. And this path here, we write it as the inverse of win person. So, okay, how does this work? Here we have our graph, and we see that this is of type Academy Best Director. So we see that we're going to target this node here. And then we say that, okay, we're targeting this node with this shape. So therefore, this node must have 1 or more win movie director. So if we go here, we see win movie, Parasite director, Bong Joon-ho. So then from there, we must go in the other direction, and we must say that this winner must have a name and a date of birth, and must have an inverse link to Academy Best Director, which we see here. So we say that it satisfies the shape. So what we haven't really required is that this is actually a triangle. We haven't said that this here must connect. So the director of the movie who wins Academy Best Director, that person must win the Academy Best Director. We haven't enforced that, just that this is of type Academy Best Director, that it satisfies the Academy Best Director shape. Not necessarily, there could have been a different Academy Best Director here. So in any case, this is valid. And we see how we can use properties. Paths, more complex paths, sorry. So here we have another example where we are going to say that Academy Best Director, Best Picture, must be an instance of Academy Best Picture, and it must have a year, which is a G year. So it has precisely one type, which is Academy Best Picture, and it has precisely 1 year, which is a XSD G year. And we use paths here to say that every Academy Best Picture must have 1 or more previous Academy Best Pictures, and must have 1 or more inverse previous, so next effectively Academy Best Pictures. And we see here how to serialize that in Shackle. So we use the 0 or more path primitive here, and 0 or more path of an inverse path of previous. So it might be a bit confusing to say an Academy Best Picture must have, each Academy Best Picture must have a previous Academy Best Picture. And you might ask, well, what about the first one? that doesn't have a previous one. However, since we use the star means itself, so it's 0 or more. So if we have the very first Academy Best Picture, it itself is connected by a 0 path, right? So it means that the first picture will still have 1 itself for a previous star, since this is 0 or more rather than 1 or more. So this actually makes sense intuitively. We would expect this to be the case. So we have our graph, and we have a bunch of Academy Best Pictures, and they're all linked by previous, and we see that they all have years. Okay, so all of them individually satisfy the conditions here. They have exactly one type, which is Academy Best Picture, and they have exactly 1 year, which is of type G year. So this looks good. So then the question is, do each of these satisfy the previous things? So as argued before, this has at least one previous, all of the previous, first of all. So if we start from this node, what it says is that this part here says that all of the previous Academy Awards Academy Best Pictures have to satisfy the shape as well. And this one does, and this one does. So it satisfies this particular path here. And then it says the inverse going in the other direction of previous. If we go 0 or more, then all of those also have to satisfy Academy Best Picture. So starting here, if we go in this direction and this direction here, then all of these also satisfy the shape, and the node itself satisfies the shape. So we say that this node satisfies the shape. Starting with this one here, we see that it has 1 or more previous star because itself counts under previous star. That satisfies the Academy Best Picture, so we're fine. And here, it has again, it counts as itself since it's star for the inverse previous. So this is also fine. So these ones are also fine by the same reasoning. So essentially what it says is that all of the nodes kind of captured here in this path of previous in this direction or in this direction are satisfy the Academy Best Picture shape. So the graph is valid. Anything that's previous or inverse previous to an Academy Best Picture satisfies the Academy Best Picture shape, and we see that that's the case. So we're good. On the other hand, if we're missing a year here, for example, then all of these nodes would fail. All of these nodes would fail because there is a node reachable by inverse previous that doesn't satisfy the Academy Best Picture shape. Okay. So, okay. Any questions or doubts? Okay, so after paths, we have shape constraints. And shape constraints are basically what we validate, right? So paths kind of tell us what nodes we want to validate, but shape constraints are going to tell us what things we're going to actually validate. So the first thing is that given a shape and a path, we can do two things. The first thing is we can just say node shape, and we can say that essentially the current, we can ignore the path effectively. We could say all target nodes satisfy the shape. So it basically says that whatever is targeted by the parent shape must also satisfy this shape. We can also say, for example, that all value nodes connected by a path E from each target node must satisfy the shape. Yeah. So the definitions are not so intuitive, but we've seen lots of examples of this. So this applies directly to the shape or to the node targeted by the shape, and this applies. This shape will be applied to all of the nodes connected via a path that matches the expression E. We'll apply this shape to that. So we've already seen plenty of examples of that. So that's here, for example, we have used the property here and then specified a shape that the things connected via that must satisfy, with the path here reflecting E, the expression that must be matched. And node here, we specify directly that the targeted instances must satisfy this shape here. So node is just directly applying this to whatever is matched. And then property is applying it to things that are connected via a path from what is matched. Okay. So if we look at this example here and we see what's targeted, we're targeting classes of Academy Award. Instances of Academy Award, apologies. And we see that we target all of these because they're not directly instances of Academy Award, but they're instances of a subclass of Academy Award. So what this means essentially is that we're going to have to check each of these against what this shape is targeting, which is Academy Award. So we're going to have to check each of these targeted nodes against this shape here. And we say that it must be, each of these must satisfy directly the award shape, which means that each of them must have a year, at least 1 year, and all years must be of G year. What else? We also say that each of these nodes here must have a winning movie, and that winning movie must satisfy the movie shape. So it means that every winning movie must have a year. Okay. So if we go through the shapes, the nodes that are targeted one by one, here we see that it has a year, which is good. It satisfies the movie shape. However, we also require that it has a winning movie, and we see that there's no winning movie here. So this node is going to fail, and it doesn't satisfy the Academy Award shape. Next, we see that we have an award. It has a year, it has a winning movie, and the winning movie has a year. So we see that this one satisfies. Next up, we have an award that has a year, but it has no winning movie. So similar to this case here, it will fail. In this case, we have a year, we have a winning movie, but the movie shape specifies, I changed this slide because I thought it was incorrect, but it's actually fine. Yeah, I was wondering what was wrong. I figured that I had checked these examples. This one is wrong. This one is not valid because the data type is not G year. So this should be incorrect because the year here is incorrect. This one is satisfied. It's going to say it's incorrect, but it's satisfied. It's satisfied because we have a year for the award and we have a winning movie. The winning movie doesn't have a year, but here there's no requirement. There's no min count. So we don't actually require the movie to have a year. We just say that if it does have a year, it must be a G year. So this one's actually valid. And the last one is invalid because it doesn't have a year. So this was actually originally correct. And then I just changed it for some unknown, oh no, I changed it for some unknown reason. So this should go over here. And this should go over here. And I'll have to change the order of the animations at some stage, but okay. This is what it should look like. So this one is correct and this one's incorrect. I should trust myself more. Okay. So we can also specify Boolean constraints on top of the shapes. So this means that if we have multiple shapes, we can combine them using Boolean conditions. So we can negate a shape to say that a node should not satisfy a given shape. We can say that a node must satisfy a list of different shapes, one of them, at least one of these shapes, or that it must satisfy all of these shapes, or that it must satisfy at least one of these shapes here. So we have these Boolean constraints we can specify on this. So for example, if we have a shape, Academy Best International Feature Film, and we say that we're targeting the analogous class, we can say that each of these movies, the movies that win this award for international feature film, they must satisfy the shape of not from the US and a feature movie, okay? Where a feature movie has the value false for short, and where not from the US means that the shape from the US says that the country property must have the value US, okay? So if we have this graph here and we see that we have this award here, which all of these awards are targeted because they're all Academy Best International Feature Films. Then we need to check that each of the movies that it is won is not from the US and it's false for short. So it's a feature length movie. So we see that this one fails because it's from the US. We see that this one fails because the movie that won is from the US. We see that this movie here, it will pass the from US, but it will fail the feature length movie. Or will it? No, it will pass the feature movie. No. There's no count, sorry, but it says has value. So it must have the value false for short. So this will fail because it doesn't have the value false for short. This award here, it's not from the US, it's from France and Italy, so we're fine. And it has the value false for short, so it's valid. And finally, this movie, although this award, although it's won by a movie not from the US, it doesn't have the value false for short, so this one will be false. Okay. So we see a shape for best international feature films and how to combine different shapes using Boolean combinations. Next, for value type constraints, we have we can specify different kinds of what kinds of values if effectively something can be or something can have on a given property. So we can specify that every node must have must be an instance of a class, for example, or it must have a data type, a particular data type, or it must be a sort of a type of RDF node, by which I mean it must be a blank node or an IRI or literal, or blank node or IRI, or blank node or literal, or an IRI or literal. So we see some example here for a person shape where we define that we're going to be targeting the objects of the win person property. And we're going to require that each of them be of an instance of person and that each of them be a blank node or an IRI, which means essentially not a literal. So we're not going to use literals for people. And then we're going to say that they have a name that's a data type string. So these are the sorts of constraints here. We've already seen examples of these. Here we're targeting objects of win person. So these are the objects of win person here. And we're saying we're going to check the first one, and it has to be an instance of person. It has to be a blank node or an IRI, and it must have a name that's a string. So by default, we'll recall that if something doesn't have a data type in RDF, a literal, it's considered to be a string by default. So we think that all of this matches, and therefore it's valid. So the next one, it's an IRI, which is fine, like node or IRI. It's an instance of person, which is good. And it must have a name that is a string. So it has one name that's a string and one name that's an integer. And in this case, it will fail because, again, the count isn't saying it must have one name that's a string. It says it must have one name. And this is in something separate. It says that all names must be strings. And we see here all names are not strings, so we fail. This guy fails because it's a literal. It's directly a literal, not a blank node or an IRI. This one passes. It's an instance of person. It has at least one name. Those names are strings. And it's itself an IRI, so that's fine. And this one here is an IRI. It has a name that's a string, but it's not an instance of person, so it will fail. So we see the different types of values, value type constraints here. We can also specify certain ranges on values. So we can specify, for example, that the Academy Best Picture, the year must be at least 1929, because that was the first time that that award was specified. So this can help us maybe to find typos in years, for example. So we can specify that all Academy Best Pictures on the property year must have a data type G year and must have at least the year 1929. We can do min inclusive, max inclusive, min exclusive, or max exclusive as we prefer. So in this case here, we have these are all instances of Academy Best Picture, which is the target class of this shape. So we say that each of these nodes in the shape must have years that correspond to this. So they must be G years and at least 1929. So this one looks okay. This one looks fine. This year, the year looks okay, but the data type is int. So this one is going to fail. This one looks problematic, right? Somehow there was a typo here. It's not at least 1929. So this is going to fail, even though the year is valid. It's just 931. It's way too early. This one here looks okay. And this one here does not have a movie. So in this case, it will be okay. So if there's no movie, we don't have a min count, then it's okay. If there's no movie, it doesn't have to satisfy this value range constraint. Any questions or doubts thus far? Okay, you can shout if you have feel free to interrupt me if you have a doubt. So for the set of nodes, what we can also specify are some values that it has to be a particular value, not an instance of a class, not an instance of a data type, not an IRI or a blank node, but really it has to have a particular value. So for example, we can say that a US movie should have a US movie is a shape, and it should satisfy that the country has the value US for that movie. So we can use has value, or we can provide a range or a list of different values it could be. So for example, we could say a North American movie must be in US, Canada, Mexico, for example. Maybe Denmark, I'm not sure. So we can list all of the different options for that. So how does this, Denmark, I mean, well, Greenland. So how does this work for value range constraints? So in general, if we have, for example, here, we're targeting movies and we're saying that all the movies must be from the US, then in this case, this will look okay because it has the value US. Mr. Vincent is correct. This one, not so. Malaga, not from the US, and Rashomon, not from the US. Now, whether or not we want to check that, whether or not this example makes sense in reality, I'm not sure, although I think most of the Academy Best Pictures are from the US. I think a couple of one that aren't from the US. I don't think it's a restriction. But okay, for the purposes of the example here, we see how to validate that the value is a particular value. We can also do constraints based on strings. So we can specify, we can apply regular expressions to strings, make sure the string has a length of at least m or at most m. And we can also specify regular expressions that the strings should match. So if we wanted to check the years, for example, we could say, okay, every year should have precisely a length of 4 by saying min length 4, max length 4. And the pattern must satisfy that it starts either with 19 or 20, and then it has two numbers that follow that. Excuse me. So, and then we specify that the regular expression will be case insensitive, which actually makes absolutely no difference here, but it's just shown for the example. So this is to validate the strings that we use for the years. So in this case here, we're going to look at the years, the lexical value, and we're going to check that it has length 4. So that's the case here. And it matches the pattern of starting with 19 or 20 and having two numbers, which is fine here. So this year looks okay. So note that we're targeting the objects of year. So we're directly targeting the year nodes in this case, the literals themselves. So in this case, 1930 looks okay, but it's an XSD int, which does not satisfy this data type constraint here. So this is going to fail. This one does not start with 19, so this one's going to fail. And this one looks okay, has length of 4, starts with 19, has two numbers following it, is a G year, so it looks okay. So we can also, specify some some constraints on data type values and strings and so forth. There's a couple of other string constraints that we can specify. For example, we can say that a particular node must have a language from one of these options. And then we can also say that the language must be unique. So it means that, for example, we can say that a name is unique for a given language, that we can have different names in different languages, but we shouldn't have two names in the same language. So two Spanish names, for example. So here we have some shape, which has the very catchy name of movie has unique English Spanish name. So where we have that the names, all of the names are either English or Spanish, and that each name is unique for that language. It's worth noting as well that ES, for example, will match the Chilean Spanish variant, or EN will match EN US, EN UK, EN IE, and so forth. So what are we checking? We're checking the objects of WinMovie, which are, again, the pink nodes here. And then we're going to say that their names, they must have language ES or EN, and they must have unique languages. So in this case, it has no name. We don't have any min count here, so that's fine. So it passes. Okay, so if there's no names, the names don't have to satisfy the constraints. We have two names. We have one in English, one in Spanish and one in English. So we're good. Here we have Bicycle Thieves, the name, but it has no language tag. So this one's going to fail. Here we have two names in Spanish, in Chilean Spanish. So this is going to break the unique language restriction. And here we have English and Japanese, and this will break the restriction that all languages are either ES or EN, Spanish or English. So here we fail. Okay. So we also have cardinality constraints, which we've seen plenty of examples of, in fact, of max count and min count, which allows us to say, for example, that best director must have at least one person who wins, right? But we can also use the qualified min count or qualified max count. And what the qualified count does is it adds a shape. And we say that there must be, in this case, at least m nodes on this property that satisfy the shape. It essentially discounts the ones that don't satisfy the shape, or it only counts those that satisfy the shape. And this says at most m nodes that satisfy this shape. So if we look here, we have a shape which says first in series. This is the one that has no previous node. So it's a max count of 0 on previous. So this is supposed to be the first thing in the series, the one that has no previous thing before it. And then we can say that an Academy Best Picture has a qualified max count and a qualified min count of 1. So it has precisely one node on a 0 or more path of previous. So it's connected recursively by previous to at most one first in series. So there must be at most one node that satisfies this shape here, which essentially says that it doesn't have anything before it. So this is kind of intuitive if we expect it to be a line, right? To be a line graph where we just have previous, 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 and so forth. So does this pass here? So we have 0 or more path of previous. So here, this node is connected by itself to this path because it's 0 or more path of previous. So this node is targeted because, first of all these nodes are targeted because they're of type Academy Best Picture, which is the target class here. So this node here has itself on the 0 path, has itself on this property. And then we have to count, does it have exactly one first in series, which means that is it connected to precisely one such node that is the first in the series? It's connected to itself and only itself, so it passes. In this case here, again, similar argument, it's connected to at most one node via recursive previous that has no previous, so it passes. In this case, we see that it connects to at least one node, but it also has this stray previous pointing to a blank node here. So now it has two things that could be counted as the first in series that don't have any previous. So this one fails. This one, again, has two because it goes this way, that's one, and it goes all the way back this way, so it also has two. And this one, again, also has two. So we see that the first two pass, and then these ones fail here because they have more than one previous, because of this weird previous node here. So the point being that with qualified max count and qualified min count, we only count the nodes that satisfy the shape. In this case, we're saying that each has precisely one, but it has precisely one that satisfies the shape, saying that the node has no previous value. So we can also relate values based on a property pair constraint. So this means, for example, that we can say that two properties must have the same value, or two properties cannot have the same value, or one property must have strictly less lower values than another property, or that one property must have lower or equals values than a property, than the values for another property. So for example, when we're defining Academy Best Picture, we could say that the year of the movie must be less than the year of the award. Less than or equals would probably make more sense in reality, but essentially, if you're winning it at the award, the 2020 award, this says here specifically that movie must be from 2019 or earlier. And disjoint. So this says essentially that here what we're doing is we're creating this path which essentially traverses previous recursively one way and recursively the other way, and it says that whatever awards we can reach through previous in one direction or the other recursively, none of those awards must have the same year. So it says that all of those years must be different to the current year. So that's this example here. So we're targeting again the instances of Academy Best Picture, and we say that the year of the movie won must be less than the year of the award. So here's the year that that we have for the award, but it has no win movie, so this passes. We have no min count here, and if there's nothing, it doesn't have to satisfy. Nothing trivially satisfies the constraints would be a better way to put it. Here we have a year, we have a movie, and the movie and the award have the same year, but here we want them to be strictly less than. Whether or not in practice this is the case, I'm not sure, but here this will fail according to what we've defined. Here we have 1931, and we say that the year of the award is 1930, but we have no movie that's winning. However, we're going to fail on the disjoint constraint because now we have a previous award has the same year as this award. So this restriction here fails. So this one fails. And this one will, we have 1932. We have a movie. The movie has no year. So we're fine. So if it has no year, we don't require it to have a year. We just say that if it has a year, it must be less than. So this is okay. And finally, this one, we have a movie. Movie has year 1932. We have no year here. So this one is also fine. So unless we have the pair, if only one of them has a year, for example, if only the movie has a year or only the award has a year, that's also considered to be validating. So I think one of the final features, let me see what time it is. My way over. I'm getting close. So we're almost done. There's a little bit left, but we can finish the class on at the start of the lab on Wednesday. So there's closed constraints and then sparkle constraints, and we're pretty much done. Any questions or doubts? Okay, so with this shapes, essentially the kind of history of the shapes is that there was lots of people publishing RDF, but how do you assure certain quality? How do you validate the RDF data? How do you say, I want, for my application, it would be great to have that everything has a name in different languages and so forth. So people decided to define this different companies and so forth got together to define the standard of shapes for validating RDF data. So in the lab on Wednesday, we'll be playing with shapes in RDF Playground with Shackle. After this, we'll be focusing mainly on projects. The other thing to mention is that we have to do the peer evaluation of the reading groups, which I'll be setting up today. I didn't want to assign the evaluations during the holidays, but so you'll be asked to look over the other reading group videos. So we'll coordinate all that by on the forum. So if there's no questions or doubts, see you on Wednesday in the lab. Okay, bye-bye. Bye-bye, thanks.
Bye-bye. Yeah.